Hello and welcome to the course. I'm glad that you're here. In this first video, I want to give a basic intuitive understanding of what large language models are doing. It's not magic, but it is based on a really complex mathematical formula really, that's only optimizing for one thing, and that is the probability of what is the next word in a sequence. Usually the sequence will start with a prompt that you give it, and then it'll start generating words from there. We're going to go over the basics of how this works. So where does a language model figure out what word comes next? Well, not surprisingly, it learns from looking at existing text. And in machine learning in general, natural language processing is based on machine learning. This is kind of the basic idea. If you have examples of something, usually you want a good number, at least of quality examples. Once you have that, you can model you can create a math model to kind of mimic that, to learn the patterns, even if humans can't really explain all of those patterns. And there are many, many patterns and many exceptions in natural language, as we all know. But this is a really key idea. So keep this in mind. We have lots of examples of text, and that's why they're large language models. They take information from all of the Wikipedia pages, open collections of books, all kinds of places, and they can learn the patterns of natural language. I found this graphic from Statista, which is a very good website, by the way, good reference. And they did a study. These were the highest number of citations that they found. Now, that's not exactly equivalent to what training text that a particular model used, but since many commercial models don't provide openly all of this information, you kind of have to back into some of it. It's quite interesting that Reddit is the #1 source. Now, that's actually not surprising when you think about Google and search engines will often show up, or Reddit. And in fact, a common search technique is simply to add the keyword Reddit to the end of any Google search or text search. But Wikipedia is #2, so that we're not surprised with because that provides a vast amount of general information, which is on average pretty good because it's got checks and balances. So of course, when you're reading information from all over the internet, there's a high probability of getting some kind of garbage information. After all, anyone can publish things on the internet. So when you think about Googling for information you're looking for, if you click on a link that kind of takes you to a garbage website, by garbage, I just mean that the information is not factually correct or completely verified. This would be equivalent, and part of the reason why you see AI hallucinations when a language model kind of makes up something. It's based on the probabilities, and if it's seeing information that isn't necessarily true, that could possibly get incorporated. There's also a randomness aspect that we're going to talk about, but I thought this was a pretty interesting graph. This diagram from a blog post by Denis Kazarov is a great illustration of what language models are doing. So if you've got a sequence of words, and really when we talk about this, transformers are the technology or the architecture that modern language models use. They're really sequence-to-sequence translators or predictors. So here you've got a sequence of words. The boy went to and you can see what the model actually does on every word, or specifically token, we'll talk about that, but on every word that it generates. It's generating a probability distribution. What's the chance of every possible word that it knows in its vocabulary, the probability that each of those could come next? So the boy went to so the highest probability here is playground. And that would come from, largely speaking, the training text that the model was trained on, but it can also come from subsequent fine-tuning and reinforcement learning that we'll talk about. That so the model doesn't just learn to understand regular or English language, but you can steer it in a particular direction, and that's where you start to see the personality behind different language models. We will talk about language training in more detail later in this course, but I wanted to briefly show you. So this is from a website that lets you run prompts on different models. So Llama is Meta's primary model, and this is their base model. That means it's just gone through the training that has learned language patterns. It hasn't been fine-tuned yet. It doesn't have a personality. And so I prompted it. I happen to live in Orlando. I asked it, what are the best things to do in Orlando this time of year? And you get reasonable English sentences here, but it's kind of a run-on paragraph. There isn't even really a paragraph structure, and it's kind of disorganized, if you will. So is it valid English? Are they valid English sentences? Yes. But if this was your chatbot, it wouldn't be people wouldn't come back to it. So let's compare this now. This is the same prompt against kind of the regular Llama 3.1 model, the equivalent, but it's been instruction tuned is how it would generally be referred to it. And you can see it's a much more user-friendly response. There's an introduction paragraph, an exclamation of excitement at the question. There's always something exciting to do in this vibrant city. And then it recognizes what time of year it is. It happens to be spring. I did this at a different time, so that's why you're seeing March to May, with a bullet pointed list of different attractions that you might be interested in. So in the control on the left there, you can also see a number of parameters of which we're going to talk about: temperature and top P. Those are ways that influence the creativity of the model. I showed you a minute ago a chart where the boy went to and the most likely next word was playground, but language models don't always choose the most probable word. And it's kind of interesting. It turns out that actually the quality of the model is better if it doesn't always do that, if there's some variance. Now, part of that is because for creative use cases, you want to get some creativity. This is also the reason why if all of us went to your favorite model, Gemini, ChatGPT, and said, write me a poem about a cat, even more specific, write me a haiku poem about a cat, we would likely all get different poems written. Even when you turn the temperature setting down to 0, there's still some element of randomness. That's just the nature of these models. Temperature is a setting that is basically a creativity fine-tune control, and it affects, it kind of evens out the probability. I'm going to show you a visual example of this in a minute, but I wanted to kind of give you kind of a quick outline of what these language models are doing. They're learning patterns of natural language and then using that to predict next words. And it's interesting because out of that emerges what seems to us like intelligence many times. Certainly they can pass the Turing test in that they can create comprehensible paragraphs and written text that could have easily been written by a human as opposed to a computer. Now, in terms of intelligence, you could say, well, does the model actually know things? Does it understand that the capital of France is Paris? Well, if you ask it what is the capital of France, it will start to generate tokens, and it understands through that sequence that it will write you a sentence that says the capital is Paris. But in terms of the actual intelligence, these are philosophical questions that we'll touch on briefly in this course, but I first want to give you this intuitive understanding of what they're actually doing. That'll give you more information. You can make those own judgments yourself. In order to show you a little bit better, I've got a Python notebook here. A Python notebook can combine documentation and code. So I'll make this available to you. But we're going to start out with, rather than a large language model, we're going to do a small language model. So small, in fact, that the entire set of sentences, or what you would call a corpus, is actually listed out here. These play buttons allow you to run the code, which is in a given cell. So I'm doing that. This is actually just parsing through those sentences, and it's getting all of the information that we need to predict or to calculate the probability, I should say. So if we run this here, now we have a number of sentences that are about cats and dogs. In fact, so we'll go back and look at it in a second. So this is simply counting the number of times that the model saw the n-gram, or this is an n-gram of length 2. So the cat. So it's seen the words sat, slept, chased, ate, and ran after that. And essentially it's taking the number of occurrences and translating that into a probability. So this is the probability distribution. Given no other training, we would then use these probabilities and we would randomly sample. So we would pick a number, and of course sat and ran have a higher probability of showing up. But remember, these models are not always predicting the most frequently occurring. If we try dog, we see dog also has similar, and then, we can go a little bit further. So the dog sat, now it's only seen 2 words in this case, sat on or sat quietly. And I suspect if we go sat on, we'll see the rug, and that's probably the end. So we have a really small, again, training corpus. It's right here. And you can see from these sentences, so both our cat and dog sentences are length 5, and that's why we saw the 5 possibilities. So now let's talk for a minute about some of these other parameters that come into play and how it predicts the next word. So by default, it's kind of calculating the probability for every possible next word in its vocabulary, but we don't consider all 50,000 or 100,000 of those. Oftentimes we only consider the top P words or tokens. So what P would be is you look at the cumulative percentage, and once you get beyond that, you would stop. So here's a case where P equals 0.9. So go until you get 90% of the probability. And you can see I'm going to start to slide this closer. Okay, now that we are at 85%, we no longer would consider the word 8. We would only consider these top 4. And you can see as we keep going, so the lower that we get here for top P, and eventually we'll get to, right? So at this point, when P is low enough, we're always going to take the most probable word. But again, that you generally don't want that, and models really will kind of protect against that. If you want more factual information, of course, you might lessen this. If you want more creative fictional stories, for example, you might set it to be higher. And we can do this for any number. We saw 5 sentences in our training corpus for dogs, so this is going to look similar. But this is a way that you can control that. And then temperature is the next thing that we're going to look at. So here we're looking at the same probabilities for our context, the cat, and our temperature is at 1, which means we're not scaling the probabilities at all. However, if we start to slide this down, so what happens, you can see on the right side here, the scaled probabilities. The more likely tokens become even more likely, meaning we're giving more credence to likely tokens, versus if we wanted to see a creative type scenario, as we increase the temperature, you can look, the red bars start to even out actually. So by the end, they're almost all equally as likely. So this is like a creativity dial for the language model. Okay, in this course, we're not going to look at a ton of code, but I do want to show you this next method, which is pretty important. So this is actual simulated logic for how we would generate the next word in our language model. This is definition of the function sample next refine. So first we get the probability distributions. We just calculated this earlier in code up above. But now step 1, we're going to apply the temperature scaling. So what I just showed you, we're going to even out those percentages in the probability distribution. We're going to scale them based on the temperature setting. Okay, now we're going to apply the top P. Remember, top P says only consider the top cumulative percentage, the specified percentage of the tokens, and that will limit our list, so that will filter it down. And then at that point, we can get those scaled weights and that shortened list of tokens, and then randomly select. So that's how we actually get our next word. This widget here is kind of now putting this all together. So starting out with the cat, I'm going to just start with the baseline temperature of 1, top P of 90. We're just going to generate some text. And so here you've got some sentences. We have a small corpus or a small vocabulary, so it's quite possible these sentences came directly out of our sample sentences. Of course, if we put the creativity up, maybe we get some different ones, and we can run this different times. We're going to get different sentences each time. And let's see if we do the animal. So you're getting different sentences. We can also take some additional steps here. So we're actually still only getting sentences of length 5 because mostly all of our sentences in our training corpus were this length, so it's going to generate the stop token at that point. But you can see how this works. If we really lower the temperature, then you should get sentences that most likely showed up in our actual training corpus, and we could compare that and see. So here's an example. A low temperature, you get more consistency. So I mentioned that the models are actually really large mathematical functions. So these models can't work directly on strings or words or text. They really need to have numbers because it is a math formula. So tokenization is one of the first things that happens, and Tick Tokenizer gives you it's a good tool. I'll provide the link that you can try out and see how does a prompt that you give it get translated into tokens for some of the popular models. It's got a lot of different models here. I'm just going to keep it on GPT-4o. And so we had said before, what is the Capital of France. Okay, so over here on the right, you can see there's 14 tokens. Now these kind of funny IM start. So different models use different special tokens, but this is indicating that this message came from the user as opposed to a system message, which would guide the model in terms of how it should respond. But here is our actual prompt. What is the capital of Florida? And you can see by the colors, basically it broke out each word into a token. And the first word, it does differentiate between capital letters and not. So what with a capital W is the first word in the sentence. And then you can see that many of the other tokens are a space, a preceding space, and then the word. And that means the word shows up in the middle of the sentence. And not only that, each of these corresponds to, so what corresponds to token ID 4827. Now, what does that mean? Well, that maps to a word embedding. This is a technology we're going to learn a little bit about in this course, but an embedding is really a long sequence of numbers. Technically, it's called a vector, but a vector is just a list of numbers that represents that word in a high dimensional space. And this high dimensional space is where the model does its calculations and kind of does its thinking, if you will. We'll see more examples of that. But I don't want you to think that the tokens are always words. They can be different sequences of characters. So if I go back over here, and actually just to make this simpler, let me get rid of that. Okay. So what about if I just start to put multiple question marks? So here, the 3 question marks all are the same token, but if I put enough, it'll eventually break them up. So there you can see it split it up into like 8 and then 2. Likewise, if you start to use sequences of numbers, or if we did a long word, let's say like Massachusetts. So the state name Massachusetts doesn't show up commonly enough in the training corpus, so it actually gets broken out into 1, 2, 4 different tokens. So that's kind of how the language model starts out, by tokenizing the prompt, converting it into tokens, and then looking up the word embedding for each of those. So let's look at the word embedding now. Now, word embeddings are often thousands of dimensions, so it would be a sequence of, let's say, 1,500 some numbers on smaller models. We can't visualize that, so what we often do is simplify things by using a technology or an algorithm such as PCA, Principal Component Analysis, and we kind of find, okay, what are the 2 most important dimensions that we can use to plot this to still capture as much variance as possible. So it's a little bit lossy. We lose some information this way, but at least it gives us an example. So these are some sample sentences that I ran through an embedding, and then I reduced the dimensions down to just 2 so I could print it. So you can see here that there are some similarities. So on the right side, the cat sat on the mat. The cat likes to sleep on the mat. So those 2 sentences are very similar to each other. And so they end up very close to each other in this high dimensional space. And you're going to see throughout machine learning and AI that distance between data points is really a measure of the similarity. And there's a saying that you can know a word by the company that it keeps. This is an infamous, I'll find who said the quote and provide that in the footnotes. That was very influential in natural language processing. So likewise with sentences as well, you can do embeddings for just singular words, which is what we saw before. Here I'm doing it for an entire sentence. You can do an entire document as well, and you get a form of similarity search. Certainly people have done that. But that's one way kind of to think about this. And within that embedding space, once you get to a particular point and then the model sees more words or is given more context, it would kind of adjust where it's focused in that embedding space. So for example, the cat sat on the mat. So if we introduce the word brown, and let's say that came up next, now we would start to shift our focus from in this high dimensional space to some dimension that influences the color, and we would move more toward the brown region of that space. Granted, that's 1 dimension out of 1,500 or so. We don't know exactly what each dimension refers to. That's up to the model to learn. And these are such large models, it's hard for any given person to understand everything that's going on. But that's kind of the idea, that it's navigating in this space. And if all of this seems strange, a little bit strange, don't worry, because we're going to talk much more about it. But I wanted to give you kind of a sense of what's going on here. Okay, so let's step back now and kind of summarize what is the main idea to take away. So these are from the notes that I'm going to provide you, but the model asks over and over again, given what I've seen so far, given the sequence of words, what word or token should come next. That starts with just your prompt. It starts to predict or generate a word, and then that additional word becomes part of the next step. It does the whole thing over again. So when you train these models, it's going to read the text from left to right like we normally would, and it's going to block out or mask the next word, and then guess. At the beginning, it's just guessing essentially what is the next word. It's going to be wrong, and that's going to adjust its model parameters or weights, which turn out to be the probabilities. And then that gets used by the model later on, along with the different parameters that you use as a user or settings to generate responses to your prompt. So we saw a little bit of that in the demo. So this was just a quick intro. I'm glad that you're in the course. Check out the notebook that goes along with this, the assignment, and I'll see you in the next video. Thanks.